In this video, I want to talk about interpreting what the gradient actually means. So what's the big deal? The gradient actually is a big deal. It's a terrific tool for computing a directional derivative, but it also plays a much larger role in the world where multivariable calculus is used, in particular in physics. In physics, we see the gradient appear in 4 of the most useful and important laws of electrodynamics. These are Maxwell's equations. We won't see a lot about Maxwell's equations in this course, but we will see a lot that has to do with the gradient, which is a key feature of Maxwell's equations. The directional derivative of f at AB is equal to the gradient of f at AB dotted with the unit vector u. I can rewrite this using what I know about working with dot products as the magnitude of the gradient of f at AB times the magnitude of the unit vector u times the cosine of theta. This is where theta is the angle between the gradient and the unit vector. This simplifies to the magnitude of the gradient of f at AB times the cosine of theta because the magnitude of a unit vector is always going to be 1. Notice here that my directional derivative will be a maximum when cosine of theta is a maximum, which is equal to 1. This means that the gradient of f at AB and the unit vector u will be in the same direction. This corresponds to a maximum rate of increase. If, on the other hand, cosine of theta is -1, we're going to get a maximum rate of decrease. This just means that my gradient of f evaluated at AB and my unit vector will be in opposite directions. And I can also see that if theta is pi halves, my dot product will go to 0, and the gradient of f evaluated at AB and the unit vector u will be orthogonal. In these directions, when the two vectors are orthogonal, there is no change in the directional derivative. So now if I use the definition of the gradient, the directional derivative can be written in slightly different form. My directional derivative of f at AB will be equal to the gradient of f at AB dotted with the unit vector u. The gradient satisfies the sum, product, and quotient rules that are analogous to those governing ordinary derivatives. So here is a summary about directions. We're going to let f be differentiable at the point AB, and we're going to insist that my gradient at AB is not equal to 0. This means that my function f has a maximum rate of increase at the point AB, and that increase lies in the direction of the gradient of f evaluated at AB. The rate of increase in this direction will be given by the magnitude of the gradient of f evaluated at AB. I also know that f will have a maximum rate of decrease at the point AB in the direction of negative the gradient of f at AB. This means that the rate of decrease in this direction is given by negative the magnitude of the gradient of f evaluated at AB. My directional derivative is 0 in any direction that is orthogonal to the gradient of f at AB. So let's work an example. If I'm given the function f of xy is equal to x squared plus 4xy minus y squared, I want to find the unit vectors that give the direction of steepest ascent and steepest descent at the point given by the coordinates 2, 1. Then I want to find a vector that points in a direction of no change in the function at that point P given by the coordinates 2, 1. My surface for this function is a hyperbolic paraboloid. The partial derivative of f with respect to x, or fx, is given by 2x plus 4y. fx evaluated at 2, 1 gives me 8. The partial of f with respect to y, or fy, is given by 4x minus 2y, and fy at 2, 1 is 6. The gradient of f evaluated at the point 2, 1 is given by the vector with components 8, 6. The direction of steepest ascent is going to be in the direction that is in the same direction as my gradient. This means that it lies in the same direction as a unit vector given by the vector components 8, 6 over the square root of 100, or a vector with components 4/5 and 3/5. The direction of steepest descent will be in the opposite direction. The negative vector u is given by the components -4/5 and -3/5. The direction with no change is any vector of v that is perpendicular to u. If it's perpendicular, I know that if I take u and dot it with the components of v, my result will be 0. So that the vector with components 4/5 and 3/5 dotted with the vector with the components v sub 1, v sub 2 will equal 0. This means that 4/5 v1 plus 3/5 v2 will be equal to 0. This means that v sub 1 will be equal to -3/4 of v sub 2. If I choose to let v2 be 1, then my vector v, which is orthogonal to u, will be given by the components -3/4 and 1. But keep in mind, any vector perpendicular to my unit vector will work. So I could keep it very simple by just using the vector with components -3/5 and 4/5. Two different ways to come up with a vector that is orthogonal to u here. Once I have this vector identified, then I have a direction in which there is no change in my directional derivative. Now remember that when we have f of x is equal to z0, where z0 is a constant, it defined what we call a level curve. This means it was a curve on a surface where all points on that curve had the same z value. We now have used gradients to identify directions where our function does not change. This means my function value is constant. So I can put that together with this idea of a level curve to get the following theorem. If I'm given a function f that is differentiable at the point AB, the line tangent to the level curve of f at the point AB is orthogonal to the gradient of f at AB, provided the gradient of f at AB is not equal to 0. Now, this also allows me to write an alternative form of the equation for the tangent line. The level curve f of xy is equal to z0 can be viewed as a level curve in the xy plane for my surface when I look down on it from above. The line tangent to the curve at AB is orthogonal to the gradient of f at AB. This means that for any point xy that lies on that tangent line, the gradient of f at AB dotted with the vector components x minus a, y minus b is going to equal 0. So that I can write the gradient of f at AB dotted with the vector with components x minus a, y minus b is equal to 0. I'm going to write my gradient out in terms of fx and fy. I'm dotting the vector with components fx at AB, fy at AB with the vector x minus a, y minus b. This means I get fx at AB times the quantity x minus a plus fy at AB times the quantity y minus b, and that is all equal to 0. This is an alternative form of an equation for the tangent line. Let's work an example. I want to consider the top half of the ellipsoid that is defined by the function f of xy is equal to the square root of the quantity 1 minus x squared over 4 minus y squared over 16. I also am given the point P with the coordinates 0 and square root of 8, and the level curve on the ellipsoid that's given by the function f of xy is equal to 1 over square root of 2. I want to compute the slope of the line that is tangent to the level curve at P and verify that the tangent line is orthogonal to the gradient at that point. I want to then give the equation of the line tangent to the curve at the point P with coordinates 0, square root of 8. My theorem tells me that the gradient and a line tangent to the level curve must be orthogonal at the point AB, which means that the dot product of the gradient and the tangent line have to be 0 at that point. So let's let z equal the square root of the quantity 1 minus x squared over 4 minus y squared over 16 and square both sides. I get z squared is equal to 1 minus x squared over 4 minus y squared over 16. I'm going to use implicit differentiation to find dz dx. On the left side, when I differentiate with respect to x, I get 2z dz dx is equal to negative x over 2. And solving for dz dx gives me negative x over 4z. If I differentiate with respect to y, I get 2z times dz dy is equal to negative y over 8, and solving for dz dy gives me minus y over 16z. At this point, I could substitute 1 over square root of 2 for z, but I'm going to leave it like this for right now. The equation of the line tangent to the level curve at the point 0 and square root of 8 is given by y prime is equal to negative fx over fy, which is equal to negative 4x over y. The tangent line has a slope of 0 at the point 0 square root of 8, and its direction will be parallel to the vector given with the components 1, 0. So my gradient of f at the point 0 square root of 8 will be given by the vector negative x over 4z, negative y over 16z, evaluated at the point 0 square root of 8, which is equal to the vector with components 0 and negative 1/4. If I dot my unit vector given with components 1, 0 with the vector with components 0, negative 1/4, I get 0. This confirms that my tangent line is orthogonal to the gradient at the point 0 square root of 8. Now finally, I want to put all these pieces together and use the alternative equation for the line tangent to the curve at a point, which is the formula fx at AB times the quantity x minus a plus fy at AB times the quantity y minus b is equal to 0. I'm going to plug in 0 for a and square root of 8 for b. I get 0 times x minus 1/4 times the quantity y minus square root of 8 is equal to 0. This reduces to the equation y is equal to square root of 8. This is the equation for the line tangent to the curve at the point 0 square root of 8. Now you get to try it. Pause the video and using the paraboloid defined by the function f of xy is equal to 16 minus x squared over 4 minus y squared over 16, and given the point P with the coordinates 2 square root of 3 and 4, and the level curve on the ellipsoid given by the function f of xy is equal to 12, compute the slope of the line tangent to the level curve at the point P, verify that the tangent line is orthogonal to the gradient at that point, and give the equation of the line tangent to the curve at the point P with coordinates 2 square root of 3, 4. When you're ready, restart the video to check your understanding. So we're using a paraboloid defined by the function f of xy is equal to 16 minus x squared over 4 minus y squared over 16. This graphs as a downward opening paraboloid. We're interested in what happens at the point P with coordinates 2 square root of 3 and 4. I'm going to plug in the value for my level curve at f of xy is equal to 12. This gives me an equation written as 12 is equal to 16 minus x squared over 4 minus y squared over 16. I can write this in standard form as 0 is equal to 28 minus x squared over 4 minus y squared over 16. Now I can take the partial derivatives with respect to x and y. Fx is given by negative x over 2. Fy is given by negative y over 8. My y prime is equal to the negative of fx over fy, which gives me negative 4x over y. Y prime evaluated at the point 2 square root of 3 and 4 gives me negative 2 square root of 3. The tangent line is parallel to the vector with components 1 and negative 2 square root of 3. This means that the gradient of f at the point 2 square root of 3 and 4 is equal to the vector negative x over 2, negative y over 8 evaluated at the point 2 square root of 3, 4, and that's going to be equal to negative square root of 3 and negative 1/2. If I dot the vector negative square root of 3 and negative 1/2 with the vector 1 and negative 2 square root of 3, I get 0. This confirms that my tangent line and my gradient are in fact orthogonal at the point 2 square root of 3 and 4. Now I want to find the equation for my line tangent to the curve at the point P. I'm going to use fx at AB times the quantity x minus a plus fy at AB times the quantity y minus b, and that's set equal to 0. I'm going to plug in 2 square root of 3 for a and 4 for b. I get negative square root of 3 times the quantity x minus 2 square root of 3 plus negative 1/2 times the quantity y minus 4 is equal to 0. This simplifies to the equation y is equal to 2 square root of 3 times x minus 16. The gradient tells me how steep my increase or decrease is along a curve on a surface. Let me know if you have any questions.